All right, let's dive right into the bloodstream and uncover one of the most amazing stories happening inside you at this very moment, how your body stops bleeding. And trust me, this isn't just some dry biological process. It's a tale of a two-faced hero, a molecular superpower that saves your life every single day. But, as we're about to find out, it also holds a pretty dangerous secret.
You know, it's a question we've all probably thought about without even realizing it. That tiny, super annoying paper cut. By all rights, it should be a total gusher. The pressure inside your blood vessels is way higher than the air pressure outside. So what's stopping that little breach from turning into a complete disaster? Well, the answer is an elegant, lightning-fast, and frankly, a genius biological system.
So it all starts right here, a tear in the wall of a blood vessel. Just picture a hole getting punched in a high-pressure pipe. Instantly, the inner layers of that vessel wall, things like collagen that are normally hidden, get exposed to the blood. This is the alarm bell, the big red distress signal that summons the first responders.
And who are these first responders? Meet the platelets, your body's microscopic emergency crew. First up is adhesion. They immediately stick to that exposed collagen like glue. Then activation. They go from these smooth little discs to spiky, sticky grappling hooks. This transformation makes them release chemical signals. And that leads to aggregation. Those signals are basically screaming for backup, and more platelets pile on, forming a quick, temporary plug. It's a decent patch, but it's not strong enough to last. For that, we're going to need the heavy machinery.
You see, floating right alongside those platelets are the system's secret weapons, the coagulation factors. Most of these are what scientists call zymogens. A good way to think of them is like highly trained secret agents just circulating in a sleeping state. They're completely harmless, until they get a very specific activation code, which usually means another enzyme comes along and snips a little piece off of them.
So how do these agents get all their cool gear? Well, it all comes down to one crucial ingredient, vitamin K. In your liver, a special enzyme uses vitamin K to give several of these key factors a critical upgrade. It creates something called a GLA domain, which is basically a molecular claw. It's perfectly shaped to grab onto calcium ions. And this little calcium bridge is what allows these factors to anchor themselves right onto the surface of the platelets at the injury site. It's simple. No vitamin K, no claw, no clot.
Okay, so we've got our emergency crew on site, and our secret agents are armed and ready to go. Now we just need to light the fuse. But this has to be an incredibly controlled explosion, right? It needs to happen only where the injury is and absolutely nowhere else.
And that tripwire is a protein called tissue factor. Now here's the cool part. It's a receptor that's normally hidden away on cells outside the blood vessels. It is never, ever supposed to come into contact with the blood. But the second that pipe is breached, tissue factor is suddenly exposed, and the moment it touches the bloodstream, the fuse is lit. This kicks off what's known as the trigger pathway. The exposed tissue factor acts like a docking station for another factor, factor 7. Together, they form the trigger complex, and its one and only job is to find and activate another factor, factor X. This activated factor X then helps create a tiny, and I mean tiny, almost insignificant amount of our story's hero, an enzyme called thrombin. This isn't the main event, this is just the thrombin spark.
But here's the thing. That tiny little spark of thrombin is all it takes to ignite an absolute firestorm of activity. The whole system is designed not just to activate, but to explode exponentially, building on itself in this brilliant feedback loop. And this is the key. Thrombin is basically its own hype man. That initial spark immediately turns around and activates a whole set of other key factors, specifically factors V, 8, and 11. This feedback loop, this self-amplification, is the secret to going from that tiny little spark to an unstoppable burst.
And this is just a beautiful illustration of how the system builds on itself. That thrombin we just made activates the parts for two critical molecular machines. First, you've got the amplifier. This machine takes newly activated factors 8 and 9, pairs them up, and together they just churn out mountains of activated factor X. Then you have the engine. It takes all that new factor X, pairs it with factor 5, and uses that combo to convert massive quantities of prothrombin into the star of our show, thrombin. And that creates the thrombin burst, a tidal wave of this active enzyme.
So,
With this huge burst of thrombin now on the scene, its main job can finally begin. It acts like a master builder with a tiny pair of molecular scissors, and it just rapidly snips up all these soluble proteins called fibrinogen into sticky fibrin strands. These strands then weave themselves into this incredible mesh that reinforces that initial platelet plug, creating a stable, rock-solid clot.
Okay, hold on. We've just built an incredibly powerful self-amplifying engine of clotting. But that raises a very, very serious question. How do you stop a superpower like this before it goes completely rogue?
Now, seriously, think about it. What stops this cascade from just continuing until your entire circulatory system is one solid block of concrete? Well, the answer is a system of brakes that is just as elegant and just as powerful as the accelerator.
So your body basically has three main braking systems. First, there's a molecule that quickly shuts down that initial tissue factor trigger. Then you've got something called antithrombin, which is like a patrolling scavenger. And finally, the protein C pathway. And this is where our story gets its big twist, because the main character in this braking system is none other than thrombin itself.
So let's look at antithrombin real quick. The best way to think of it is as a molecular venous flytrap. It just floats to your blood, and if it bumps into an active clotting enzyme that's drifted away from the main clot, it just snaps shut, trapping and neutralizing it for good. It is your blood's very own cleanup crew.
And now we get to the climax of our story, the great reveal. We have seen thrombin as the hero, the one who builds the clot. But it has another identity, a second face, that is the complete and total opposite of the first.
So here's how it works. When thrombin, our pro-clotting hero, drifts away from the injury and comes into contact with the smooth, healthy lining of the vessel wall, it finds a receptor waiting for it called thrombomodulin. And the moment thrombin binds to that receptor, its entire personality changes. Its function does a complete 180-degree flip. And this is where we see the two faces of our hero side by side. At the site of the injury, thrombin is a pro-clotting beast. It makes fibrin, it fires up platelets, it amplifies its own production. But when it's bound to thrombomodulin on healthy cells, it becomes a powerful anticoagulant. It can't build a clot anymore. Instead, its new job is to activate a molecule called protein C, which then goes and destroys those key factors V and 8, effectively slamming the brakes on the whole cascade. The hero becomes the regulator, making sure the clot stays exactly where it needs to be and doesn't spread.
So the most important takeaway is this. The coagulation cascade isn't just a gas pedal, it's a high-performance system with an equally sophisticated set of brakes. The accelerator and the brakes are completely interconnected, and they often use the very same components, like thrombin, to achieve this perfect, life-sustaining balance.
This elegant dance between making a clot and controlling it is what keeps us alive every single day. Which leaves us with one last critical question. What happens when that balance gets tipped? What happens when the accelerator gets stuck on? Or when the brakes completely fail? Well, that's where things get really dangerous. And that is a story for another time.